So now what we're going to do is talk about the anatomy of the atom. And as we know, the atom is made up of protons, neutrons, and electrons. The electrons have a negative charge, protons are positively charged, and the neutrons have no charge. And that's Sheldon's favorite joke. Neutron walks into a bar, he asks the bartender, how much for that drink? Bartender says, for you, no charge. Ba-dum-bum. We also know that protons and neutrons are much heavier than electrons. Actually, electrons are around 1,836 times the size of protons. We also know that protons and neutrons are made up of quarks, and they're kind of held together by gluons. Now, one thing about electrons is that when you look at it under an electronic microscope, you actually don't see a one particular electron. You actually see a cloud of electrons. And basically what that means is that an electron exists over here, it exists over here, it exists over here, it exists over here. This means that an electron could actually exist in two places or more at the same time. This kind of brings us to something called quantum entanglement. Let's say you have two atomic particles. They exist over here. If they become close enough, they actually become one particle. And if you take this particle and you move it over here, whatever you do to the partner particle instantaneously will have an effect on this particular particle. So I think what's happening is that a particle can actually exist in two spaces at a single moment in time. Now, in particle physics and quantum physics, a particle can have a spin, and that spin is either up or down. And as soon as you measure a particular particle, and let's say that spin is up, immediately its partner particle will have the opposite spin. Now, Einstein says that nothing travels faster than the speed of light. But it doesn't take the speed of light, it doesn't take that time to actually affect the particle over here. It happens instantaneously. So what I think is happening is that the particles actually exist in two different places at the same time. So it's occupying two different spaces at the same time. And that's why if you do something to one, it automatically affects the other instantaneously. But let's get back to our atom again. So some people think that matter is made up of little strings of energy. So if you take a picture of a proton or a neutron or electron and you go smaller and you go smaller and even more smaller, eventually what you're going to do is you're going to find strings of energy. That theory is called superstring theory. And basically what it says is that all matter is made up of elongated one-dimensional strings. Now, that theory was put forth by C.N. Chang of the Stony Brook Institute in New York. So let's keep that in mind for the next slide. Einstein suggests that matter and energy are two different sides of the same coin, E equals mc squared. And basically what he suggests is that energy is interchangeable with matter. And when you turn matter into energy, what happens is that you lose energy at the rate of the speed of light squared. Now, let's assume that the string theorists were right, and we have these strings of energy, and they're held together by these particular strings of energy. And when you lose, let's say, half of the matter, all of this turns into energy at the rate of c squared. By the way, c squared just means the speed of light squared. So you can imagine that the speed of light squared is a massive number. And what I think happens is that eventually what you're going to do is you're going to lose enough of the energy holding these things together and the mass. And what happens is that matter actually turns into smaller and smaller particles of matter, and let's call that dark matter, right? And then what happens eventually is that there is no more of these strings that hold the superstrings together. They are all gone, and basically all you're left is with strings of energy. Okay? And let's assume, for the sake of argument, that these strings of energy and the dark matter, for example, they don't reflect light. Now, a lot of scientists says that, well, they don't interact with light. I'm not quite sure if that's true or not, but what we do know is that they don't reflect light. That's why they're called dark. Dark matter, dark energy. The other thing to keep in mind is that the matter here gives off electromagnetic radiation. Electromagnetic radiation. And that could be in the form of light, heat, radiation, okay? And basically, it has a temperature to it. Dark matter probably has a temperature to it as well, but it is cold. I would imagine that it's only a couple of degrees, maybe 10 degrees above 0 Kelvin. And dark energy, because it has no strings, it doesn't give off any electromagnetic radiation. So it is about as cold to 0 Kelvin as you're going to get. Okay, one more concept and then we'll get to the meat of the idea. And that is the birth of a black hole. And basically you have this super mass here. And when I mean super, I mean, let's say 1 million times the size of our sun. And the way to talk about that is 1 million solar mass. Okay? Some people think that in the middle of a black hole, there might be a object that has 1 billion solar masses. Now, basically what that means is that whatever is in the center of that black hole is 1 billion times more massive than our sun. So basically we start off with this object that is made up of hydrogen. And at the center, at this core, it is so hot that it fuses hydrogen atoms and forms helium. So it talks like this. That's my helium impression, not Michael Jackson. So what's happening right now is that you have nuclear explosions. When this occur, you have massive amounts of light radiation coming off of this particular planet. And right now, there is a balance, perfect balance, between the outward push of the explosions and the inward pull of gravity. So the star actually stays intact. Now, as you go up the periodic table, this star uses up its energy. And what happens in that particular case is that the explosions actually outweigh gravity. So the star is going to expand. Okay? Eventually, these reactions continue until you get to iron. And after iron, the star just loses its energy. There's no more energy produced. So what happens is that it just collapses into itself until it has this massive explosion. Okay? That's called a supernova. And then what happens is that the core of the star is still intact and then pulls all of the matter back into it until it becomes something the size, maybe 1/millionth the size of the Earth. But don't forget, it still has a billion solar mass. So what happens is that this particular object is now so dense that it bends space and time. Now, if I'm on Earth and I throw an object up, so I'm on Earth, I throw an object, that object is going to fall back to Earth. If I throw it a little further, it goes further and it falls back. But let's say I was Superman and I was able to throw that ball so it can actually escape the gravitational pull of Earth. It'll actually fly into space and keep going. But this particular object bends space and time so much that not even the speed of light can escape the gravitational pull of that particular object. And what happens is that actually forms a black hole. Now, there's a couple of things with a black hole. This is called the event horizon, and that is the point in time, that is the point in space where light from here can actually escape the black hole, but anything south of there will not be able to escape the pull, the gravitational pull of that particular object. So basically, that's why a black hole is black. The other important part of black hole is right in the middle of that object, where gravity is the strongest. It's called the singularity. And that is a very, very tiny, tiny, tiny point in space and time. Okay? Now don't forget that this star has collapsed. It is about 1 billion times, or in this case 1 million times, solar mass. But it's also it's 1 million times the size of the Earth. So what I think happens is that it splits both space and time.